Hello and welcome to another live stream. This is Chemistry 222 now, and I hope you all had a wonderful Chemistry 221 on our raring to go for Chemistry 222. Again, my name is Travis, and I'm bringing you these live streams thanks to Portland State University's Learning Center and the Chemistry Department. To start off with, I like to post a few links in the chat window. These are links to the Learning Center's website, Facebook, and Instagram, so follow them on Facebook and Instagram and check out their website, as well as you can check out the Portland State's YouTube channel, the Learning Center's YouTube channel at least, which you can find recordings of all of these videos posted on there I usually post them the same day that I put them up there. So hopefully all of those are up there. There should be a playlist for all the Chemistry 222 ones, and you can also look back on the Chemistry 221 ones that we did previously. Today we're going to be talking a lot about calorimetry and enthalpy. So basically how thermal heat exchanges work and what the values are of, what am I saying? What the values of enthalpy is, and for the different types of reactions that we have, the reactions of formation, reactions of change, and stuff like that. So let's jump in and get started with that. First problem I'm looking at is problem 4 from the OpenStax Chemistry 2E textbook. We're going to calculate the heat capacity in joules and calories per degree for the following things. First one's for water, the second one's for lead. So for part A, there we are. So we know that to find the heat capacity, basically we use the same equation we're going to use a lot today. That's Q is equal to mc delta T. So where Q is the heat energy that we're looking at, m is the mass of the object, C is the specific heat, and the delta T is the change in temperature. That change in temperature usually wants to be in Kelvin or degrees Celsius. We don't want it in Fahrenheit. Since Kelvin and Celsius both have the same intervals, we can use either or as long as it's the change in temperature. Anytime you have the actual temperature, you're almost always going to want to use Kelvin. So if all else fails, convert everything to Kelvin is the short answer there. So one thing, to solve this problem, we want to find all of these values here. So they're giving us the mass and what type of molecules they are. So in this case, we can use that to determine the specific heat of things. And that specific heat for water specific is something that's very common. You're going to use that a lot, so it's a good thing to kind of memorize. So the specific heat of water is equal to 4.184, and the units for that is joules per, say, degrees Celsius times grams. So we can multiply that by a mass in this case, and we can get the joules per degree. And if we multiply it by a change in temperature, we end up with the joules, which is our unit for that heat energy that we have there. So in this case, that per degree that they're saying about says that they're not worrying about the change in energy, so we can move that to one side. So taking our Q is equal to MCAT. I usually call it MCAT, so that's that delta T. We can change that a little bit and look at the Q over delta T, which is equal to the mass times the specific heat. So in this case, knowing the specific heat of water and then knowing the mass of that water as 28.4, we can easily determine what that's going to be. So that's just 28.4 grams times 4.184 joules per grams degrees Celsius. So if we multiply that up, well, oh, where'd my calculator go? There it is. We get 28.4 times 4.184 is equal to, that's going to be 119. The units for that is going to be joules per degree Celsius, because our grams are going to cancel out there. So that's going to be the heat capacity of the water. So for part B, we need to find the heat capacity of lead. And they're telling us 1 ounce of lead. So to do that, we have to do a little bit of unit conversion. So to convert 1 ounce of lead to grams, we can use the conversion that 28.35 grams is equal to 1 ounce. So using that conversion, we can then say that 1 ounce of lead, I'll say PB, which is lead, we can multiply that times 28, oops, my 2 did not look like a 2, 0.35 grams per ounce. And you see unit-wise, those ounces are going to cancel. And we'll see that we get 28.35 grams. So looking back at part A, we can see that that was about an ounce of water anyways. That's going to be an ounce as in weight, not or mass, not an ounce as in fluid ounces. They're a little bit different there. So now that we have the mass, and this is going to be the mass of iron or lead, right? Lead. So now we have the mass, we just need to find that specific heat. To find the specific heat, we can go on, there's a table in the textbook that I found, and I'd lost it. I need to find it again. There we are. And I'll switch over to that window. Oh, it's not there. Oh, that's not good. 1 second while I have a technical difficulty. My window disappeared. Trying to add it back in, and for some reason it's not wanting to come up. Add a new source. There it is. Anyway, so now we can see it, fit it to the screen. There we go. So you can see on there, especially if I do a quick little zoom, that lead has a specific heat of 0.13. So just looking those up in the table, we can find the values that we need for there. And that's going to be in section 5.1 of that textbook, OpenStax. So using that value, switching back to my iPad, we can say, so I would say C of PB is equal to 0.130. And the units for that is going to be joules per degree C. So using that, we can find that heat capacity of there. So just multiplying those values together, that's going to be 28.35 grams times, should be, yeah, 0.130 joules per grams degrees Celsius. So doing that math there, we can see that's 28.35 times 0.13 is equal to 3.69. Again, joules per degree Celsius, canceling out the grams. So the one thing, so this is all basically telling us joules per degree and joules per degree. But the question was also asking for calories per degree. We did joules. So we need to convert those joules now to calories. And the conversion rate for that, because the definition of a calorie is how much energy it takes to heat up water by 1 degree. So we can say the conversion of this is really going to be, we have to multiply that. So 119 joules per degree C. We multiply that times 4.184 joules per calorie. because that's how much energy it takes to heat up that water. That's why it's the specific heat of that. So if we did that, we're really dividing that value divided by 4.184, which is then equal to 28.4 calories. Doing the same thing for this value down here, that's 3.69 joules per degree C. And that's calorie per degree Celsius. We can multiply that times calories over 4.8184 joules, and we will get, so that's this value divided by 4.184. That's going to equal 0.881 calories per degree C. So now we've solved for the heat capacity in joules per degree C and the heat capacity for calories per degree C. This next question says, how many milliliters of water at 23 degrees Celsius with a density of 1.00 grams per milliliter must be mixed with 180 milliliters, which is about, they said, 6 ounces of coffee at 95 degrees C, so that the resulting combination will have a temperature of 60 degrees Celsius. So there's a lot going on here. They want us to assume that the coffee and water have the same density, which is useful, and the same specific heat. So the density, they tell us, is up here. And the specific heat is, of course, 4.184 joules per gram degree C. We're going to use that number a lot, which is why I say it's a good number to memorize. So they want to know how many milliliters of water that's going to be. And we can, so we have to kind of convert that into grams of water, essentially, using the density. But luckily, the density of water is 1 gram per milliliter, which makes our life a lot easier. So we can say that for every milliliter of water, you have a gram of water, so those numbers are kind of the same number when it comes down to it. But we do have to convert the 180 milliliters of coffee into grams as well. So we're basically using this idea that the Q of water, the heat capacity of water, plus the heat capacity of coffee, when they're mixed together, they're going to come to that equilibrium, and they're going to equal 0. So what's happening is the water, since it starts off cooler, is going to gain energy, while the coffee, which starts out hotter, is going to lose that heat energy. And they're going to come to this equilibrium point in between. So because of this, I can rewrite this equation saying that QW is going to be equal to the negative QC. So that just moving that QC to the other side of the equation, we set them equal to each other. And now we can break them down based off of our standard formula. Q is equal to MCAT. MC delta T. So the mass, the specific heat, and the change in temperature is really what's going to determine this. And we can use that to then solve for how much water we really need to put in there to make that temperature change be what it is. They're telling us here, basically the mass of coffee is 180 milliliters. They're telling us the initial temperature of the coffee, that's TI, basically the initial temperature. They're telling us the initial temperature of the water is 23 degrees Celsius. They tell us the final temperature of all of them is 60. Okay, and that's going to be for both liquids, right? Both of them are going to end up at that same final temperature. So we can use that. So rewriting this equation here, I can say the mass of the water times the specific heat of water, which is going to be the same as coffee, so I'm just going to leave it C, times the change in temperature. So that's always temperature final minus temperature initial, in this case of water, is going to equal the negative of the mass of coffee times the specific heat times the temperature final, which is the same for coffee and water, minus the initial temperature of coffee. And since we have this C value, that specific heat in both, we can divide both of them by C, and those will cancel out. So that means all we really need to do is solve for this mass of water here, because that's what they're asking for. So to do that, we can then divide each side by TF minus TIW. That's the final temperature minus the initial temperature of water. Notice those are going to cancel out there. Just rewriting that, I'm now solved for my mass of my water, which is then equal to the negative of the mass of the coffee times the final temperature minus the initial temperature of the coffee divided by the final temperature, minus the initial of the water. Now that we have that set up just right, we just have to plug in the values that we have. So the mass of the coffee, we said, is 180 milliliters times, the density of coffee, which is 1 gram per milliliter, giving us 180 grams. Which is equal to my mass of coffee. My temperature final, we said, is 60 degrees C. My temperature initial for the coffee is 95 degrees C. Notice this top value is going to be negative, which is going to multiply by that negative, give us a positive value at the end of the day, which is good because you can't have negative mass, right? It's just a good check. And then the temperature initial of water is going to equal 23 degrees Celsius. So plugging those values in here, I know that my mass of my water is equal to the negative mass of coffee times 60 degrees C minus 95 degrees C divided by 60 degrees C minus 23 degrees C. There we go. Notice unit-wise, all these degrees C are going to cancel each other out, and we're going to end up with just grams for our units. I always like to double check my units to make sure. And for that mass of the coffee, we can actually put in the mass because we have that at 180 grams. So now it's calculator time. That's 180. Should put a negative in front of that. Times, put a parenthesis for 60 minus 95. And I'm going to divide by, open my parentheses again, 60 minus 23. There it is. This is all equal to 170.3. I'll just leave it there. Milliliters for 3 sig figs. And really, this is 170 grams, I should say. But they're asking us how many milliliters, and we know that we can then multiply this times our conversion factor of milliliters per gram. It 1 gram per milliliter to give us 170 milliliters of water. And that's how much water we would need to put in to get that proper temperature in there. The next problem I'm going to look at is problem 22. In this problem, a 70.0 gram piece of metal at 80 degrees Celsius is placed in 100 grams of water at 22 degrees Celsius. It's contained in a calorimeter. I can never pronounce that word properly, like is shown in this figure here. I copied that figure down. Something you should be fairly familiar with at this point if you've gone through the lectures and stuff like that, or if you're doing it in the lab. It's basically a couple coffee cups to make sure it's thermally insulated, and then we have this water in there. And then you have a stir that's basically stirring it. It's stirring it enough to keep that heat uniform throughout the whole liquid, but not enough to really heat it up or add some energy to it. And then we have a thermometer in there. So we can see as we add a chemical reaction, or if we add other liquids together, we can see what that effect is in the change here. Here they're just putting a heated piece of metal in there and letting the temperature come to an equilibrium. So the metal and the water come to the same temperature, that equilibrium, at 24.6 degrees Celsius. How much heat did the metal give up to the water, and what is the specific heat of the metal? Those are the two things we need to find out. How much heat the metal lost to the water, and what's that specific heat? So just like before, it all comes down to this Q equals MCAT. So we need to figure out the mass, specific heat, and change in temperature for all of these things, both the water and the metal. And what they don't tell us is, well, what is the specific heat of the metal? So we can't use that to determine anything just yet. But we do know, since it's coming to an equilibrium, that the Q of the water plus the Q of the, I'll say the metal, needs to equal 0. Which means, again, rearranging, Q of the water is equal to the negative of the Q of the metal. So when they ask how much heat did the metal give up to the water, notice it's a negative value. That heat's going down. It's losing energy to the water. So we can just solve for the QW, and we can figure out how much that's going to be. So that's pretty straightforward. We take the mass of the water, we multiply it by the specific heat of water, and then the change in temperature. T final minus T initial. So writing in the values for that, the mass of the water is 100 grams. That's 100 grams. Multiply that by our 4.184, and the units for that is joules per gram degrees C. And then multiplying times that change in temperature. So the final is 24.6 degrees C, and the initial of the water is 22.0. Excuse me. So we can do that math. That's 100 times 4.184 times, put a parenthesis in. Parentheses are your friend. Do not forget them. And we get, this is equal to about 109 joules. Just if I'm keeping 3 sig figs. In this problem, I could just round this to 100 joules, because this 100 grams did not have that little decimal place next to it. So realistically, we're really going to 1 sig fig, but I always feel like things are horribly inaccurate if you're doing 1 sig fig. But that would be the proper way to do it. But you don't want to have that rounding error going into the next part when you find the specific heat of the metal. Because now that we know that that's how much energy is lost, we can plug that in to a negative 100, or say 109 joules, is going to equal the mass of the metal times the specific heat of the metal times the final temperature minus the initial temperature of the metal. So we can utilize that to the answer from the previous one and just plug in that value. So doing that, we know that the mass of the metal was 70.0 grams. So I'm just going to rewrite this. 109 joules is equal to 70.0 grams times the specific heat of the metal, which is really what we're trying to find out, times the final temperature, 24.6 degrees C, minus the initial temperature, which was 80 degrees C. So we can solve for that by dividing by those other two factors over to the left-hand side. So that's negative 109 joules divided by 70.0 grams times 24.6 degrees C minus 80 degrees C. Extend. And that's going to equal my specific heat. So in doing that, I'm going to grab the value I had from before so I don't have that rounding error. And then I'm going to divide by, got to put my parentheses in to make sure I'm dividing by the whole denominator here. 70.0. Put another one in there because I'm not going to bother distributing it. Let the calculator do that for me. And I forgot my negative sign. So remember that negative that we had in there originally. Just to make it proper, I need to put it in there. And this is going to be equal to 0.281. Unit-wise, we're looking at joules per grams Celsius, which is just what it should be. And now we have the specific heat of the metal. Here's another calorimetry problem. Here we have a 0.5 gram sample of KCl being added to 50 grams of water in the calorimeter. If the temperature decreases by 1.05 degrees Celsius, what is the approximate amount of heat involved in the dissolution of KCl? So we assume that the specific heat of the resulting solution is 4.18 joules per gram Celsius. And they want to know, is this reaction exothermic or endothermic? So one thing that I like to say is this specific heat, they took 1 decimal place off because it's a solution at that point. So they just basically made it a little less accurate, and that works. I'm going to make a similar assumption later on. And they're telling us that what's happening is we put that KCl into the water and there's a reaction happening. And in that reaction, there's an energy change. And that energy is causing the temperature to decrease by 1.05 degrees Celsius, which means that reaction took some of the energy out of the water and cooled the water down. So just looking at how that's supposed to work, we can tell whether it's exothermic or endothermic because that reaction absorbed energy from its surrounding area. And that absorption is going to be a endothermic reaction. If it were to get hotter, it would be an exothermic reaction. So I know that this is going to be an endothermic reaction, which means the energy that's going to take place there is going to be a negative value. We'll circle around it. So we can do the math, and the math will kind of prove to us that that's the case. So just looking, we know based on the problem, my delta T is equal to 1.05 degrees Celsius. Here, they didn't give you the final and the initial. They just told you what that decrease was. So that said, we can then plug that into our Q equals MCAT. So the mass of the solution, we had 50 grams of water, but we also had 0.5 grams of KCl. So the mass, I'm going to put the solution is equal to 50.0 grams plus 0.500 grams. We are then going to the specific heat of water. I'm going to use that, which is 4.184 joules per grams degrees Celsius. Again, see how many times we use that. It's very often. We're doing a lot of things in water. We use water as a solvent pretty often. So it's really a useful thing to have when you're trying to use the specific heat of things. We know the delta T, so now we can just plug in what this is. This up here is going to equal 50.5 grams. And notice I kind of truncated it after the first decimal place. That's the sig figs working together. Okay, with that common decimal place is the last thing that we do. So that's going to be 50.5 grams times 4.18. Put that extra 4 in there. I shouldn't have, because we are talking about a solution in this case. That gave us that specific heat to use. Joules per grams degrees Celsius. Multiply by negative 1.05 degrees C. Notice that I put this as a positive value, but really should be a negative because it's decreasing. It's decreasing by 1.05. And we can solve that to find Q. So then Q is going to be equal to 50.5 times 4.184 times a negative 105, 1.05 is equal to negative 2. Too many decimal places. 222. Leave it at 3 significant figures. The units on that, if I do my cancellations, it's joules. Just what it's supposed to be. So that's the heat capacity there. That's how much heat was basically lost in the reaction. And we can see also that it is a negative value. And that's what we predicted it should be, saying that it was endothermic, right? Because the temperature is going down, the reaction is absorbing that energy. This next one involves that instant cold packs. I'm sure you guys have seen. It's basically at room temperature, it works great, and then you break it, and it gets really cold as you mix it up. How that works is you basically have this ammonium nitrate packet in the middle or on the outside, and the inside has water. So you break that water packet a little bit and mix it up, and this reaction happens and it starts to get really cold. And we can see that what's basically happening is it's a chemical reaction that's pulling the energy out of the water, making it get really cold. And they're saying that what we have is 3.21 grams of that ammonium nitrate, which dissolves in 50.0 grams of water. That water starts out basically at room temperature at 24.9 degrees Celsius. The temperature then decreases to 20.3 degrees Celsius. So it's telling us our final temperature, our initial temperature. This is the mass of the water. And then we're going to add to that the mass of the ammonium nitrate. And they want us to calculate the Q for this reaction and explain the meaning of its arithmetic sign. So just like we did in the last question, the arithmetic sign is basically going to tell us whether it's endothermic or exothermic. And we can state any assumptions that we might have made. Now, since we know this is going to be a cold pack, it's going to get colder, which means it's going to absorb some of the energy that's inside that water. It has to be an endothermic reaction. It needs to absorb that energy. We can see that at the end by making sure we have a negative sign on our Q value. So it should be a negative change in energy, essentially. So using that same equation, Q is equal to the mass times the specific heat times the change in temperature, we can solve this problem. I'm going to write the change in temperature as final minus initial. And then we can start plugging in values. So the mass in this case of our solution is going to be equal to 50.0 grams. We're going to add to that the 3.21 grams of our ammonium nitrate. That's the total mass of everything. And this is going to be 53.21 grams. The specific heat, in this case, I'm going to assume it's about the same as what we had before, because the water itself is the thing we're really looking at, and the ions are floating around in there, but it's going to be pretty close to 4.18 joules per gram Celsius degree. So based on that, we can also see that the T final is going to equal 20.3 degrees C, which they gave us here. The T initial they gave us as well, which is equal to 24.9 degrees C. And now we can plug everything into our equation. So all of these types of problems, it comes down to how to utilize those equations, rearrange it so we can solve for what we're missing, and finding the values that we need to find. So to plug all these in, that's going to be 53.21 grams. I'm going to multiply that by the specific heat, 4.18. This is my assumption. I'm assuming that you add 3 grams of ammonium nitrate into 50 grams of water, and you're not changing its specific heat too much. So I dropped 1 sig fig, so it's a decent approximation, basically. And then my T final is going to be 20.3 degrees Celsius. We're going to subtract from that my T initial, and we should find our value for Q. That's a G. Okay. There's a Q. Notice also that since this is a greater value, we're subtracting it from 20.3, we're going to have a negative delta T there. That negative delta T is going to make this value negative, showing us that endothermic reaction. So that's 53.21 times 4.184 times, put some parentheses in, 20.3 minus 24.9. And that's going to equal a negative 1024 joules. Looking at significant figures, I have 3 figs, 3 figs, and 3 figs, so I should round to 3 significant figures essentially. The way to do that is I would say it's 1.02 times 10 to the 3rd joules, or you could even say 1.02 kilojoules. This problem, one of the questions in the back of the book there says, for problem 29, do the same example we just did, but it's using 100 grams of water instead of 50 grams of water. So you can go back and see the only real difference is we're changing this value, which changes this value and this value. So by increasing that, we're essentially going to increase, oops, this should be negative, increase the energy that's there. But you can do that math on your own and figure that out. Looking at number 64 now, we're going to switch over to enthalpy. Enthalpy is a way to determine kind of the energy that's either absorbed or released by a chemical reaction. Again, these negative values of enthalpy, these are the kind of change in enthalpy, they are going to be endothermic. So they're absorbing energy from their surrounding areas as that reaction happens. Most reactions are going to be endothermic that I've seen, where you have to mix some things into solution and heat it up slightly. So you have to add that heat into it to make that reaction happen. An example of like an exothermic reaction was, things that explode, things that blow up, anything that gets warm to the touch as the reaction's happening, it's going to be exothermic. It's harder to see that temperature change in endothermic reactions when you're making it happen, because unless it happens at room temperature, like the ice pack, you're usually heating it up. So as you're heating it up, basically it just slows the heating process a bit as the reaction starts to happen. But in this case, we can determine these fairly simply. All we're really doing is taking the sum of these two enthalpies. It's always going to be kind of this, write it here, summation of the delta H of the products minus the summation of the delta H of the reactants. Or in this case, since this is really a two-stage process, should be a summation, we're really just going to add these two values together, because that's the enthalpy for this top one and the enthalpy for that bottom one. This is really a two-stage process, so we can kind of cancel out that intermediate product / reactant to get what they're asking for up here. And that gives us this, the net ionic equation is what gives us this equation up here. And so that's pretty straightforward in this case. Sometimes we have to do a little bit of algebraic manipulation to get to that point. So to do that, really, erase that. all we have to do is take the negative 206.0 kilojoules, and we need to add to that a negative 776.8 kilojoules. And when we do that, plus negative 776.8, we get 983 kilojoules. It's a negative 983. So we had two endothermic reactions that gave us the net reaction of an endothermic reaction. Sometimes if you have one endothermic, one exothermic, it ends up being either endothermic or exothermic depending on which one's greater. This next problem, number 66, this one we have to do a little bit of manipulation because we can see this equation, they really want to see that reaction doesn't have this compound in it. So we need to manipulate it a little bit to get rid of that compound entirely. And the easy way to do that is just multiply this top one by 3. When we do that, we also have to multiply the enthalpy by 3 as well, because we're saying that reaction is going to happen 3 times as much, okay, which essentially changes the stoichiometric numbers. So it's 3, say 3 halves, and 3 there. So it lets us cancel out those all together, and it gives us a kind of a net reaction, in this case, of 3 cobalt solid plus, I'm going to add those O2s together. Adding that together, it's 4 over 2, which is the same as 2 O2 gas, which produces CO3O4 solid. But notice that our reaction is happening in the wrong direction, which means we need to flip the entire reaction around. When we flip that, really, we also have to change the signs. Multiply each of these now by a negative 1. Changing the endothermic to exothermic, so now the reaction's happening in the opposite way. So then I can rewrite this as CO3O4 solid is breaking up into 3CO solid plus 2 O2 gas. And that's what we had up top. So now that we have it in the right order and we've canceled out the right things, we can go ahead and add these enthalpies together. So in adding these together, I can say this is going to be the same as 3 times 237.9 kilojoules plus 177.5 kilojoules. Again, I changed the signs to positive, basically, by multiplying it by that negative 1, and I've tripled the top enthalpy to correspond with the fact that I had to triple this to cancel out those cobalt oxides. So adding these values together now, that's 3 times 237.9 plus 177.5. This is equal to 891.2 kilojoules. Notice it's a positive value again because we flipped that, so that's going to be an exothermic reaction. This next problem, it's actually the last problem I'm going to cover today. There's 4 parts to it. The first few are fairly simplistic. The next few are a little bit harder. And this is kind of what I was saying before, where it's the summation of the delta H degrees of formation. We say delta H of the products minus the summation delta H standard of the reactants. Because once it's produced, it has this kind of final change in enthalpy, and we can subtract out of that the enthalpy of the initial reactants from that to find out what that change in enthalpy really is for this reaction. And when we do this, we really have to look at the delta H of formation for all of these products in here. And the delta H of formation is really based off of the energy it takes to change it from its elemental form into the compound that we're talking about. So anything that's in its elemental form, such as hydrogen gas, nitrogen gas, oxygen gas, any of the solids, elemental solids, they're all going to be have a change in enthalpy of 0, because that's our baseline and everything's going to be relative to that. So in part A, we have that N2 gas plus O2 gas, which is producing 2 NO gas. So in this case, if we looked up the delta H here, we can see, and I'll pop over, assuming my browser window still works. There we are. Let's go here. Hey, it still works. So we can go over Appendix G in the OpenStax textbook. It has a bunch of these delta H's listed, and they're listed based on substance. So in this case, if I'm looking for nitrogen, I can scroll down to where it has nitrogen, and I've highlighted some of these so they're a bit easier to find. We can find your N2 gas. So here's the nitrogen. Everything under here has nitrogen in it, and we can see that there's 0 change in enthalpy for the elemental nitrogen, but the NO gas has 90.25. So I'm going to write that down here. That's 90.25. The units for this, you can see at the top of this, that's kilojoules per mole. Kilojoules per mole. So they give you this value, and you have to determine how many moles of the substance you have, and you can multiply it by this to figure out your energy. And again, nitrogen was 0. We'll find the same for oxygen when we look it up, because O2 is elemental oxygen. And I should switch back to my iPad. There it is. So O2 is elemental oxygen, so that's going to have a change in enthalpy of 0 as well. In this case, we have 2 moles of NO. So we have to multiply this value by 2. And that way, we can see that the delta H is going to equal just 90. Oops, sorry. Multiply that by 2, you should get what, 180.5. Yeah. And keep my 4 sig figs that are on there. And this should be kilojoules, because this is really 2 moles, and those cancel out. And there we can find our delta H in that sense. For part B, we have something similar. It's fairly simplistic because we have silicon, solid. Okay, that's going to be elemental silicon. If you have just one atom, or sorry, just one element in your compound, it's most likely going to be the elemental version of that, as long as it's the right phase at room temperature. So in this case, silicon is solid at room temperature, and chlorine gas is a gas at room temperature. Chlorine is gas. So we can say, when we write these down, Si solid plus 2Cl2 gas, which produces SiCl4 gas. This is going to be elemental, and this is going to be elemental. And we can see on our periodic table, if I can, where did I put my periodic tables at? I lost them. Anyway, let's go back to 22. You can see on your periodic table, some of the good ones actually have which ones are liquid, solid, and gas at room temperature. So it's a nice thing to recognize as well. You can always look up that delta H and then see that it's 0 on there. Then you'll see, oh, this is the right form of it. But we do need to look up that silicon tetrachloride. So switching back over here, we can find silicon tetrachloride. I've highlighted it there. It's got negative 687 kilojoules per mole. So in this case, that's going to be our answer. Negative 687 kilojoules per mole. I gotta switch back. Because all of the products, all the reactants in this case were elemental, there's no change in enthalpy for those. For part C, we have iron 2 trioxide. So for this, and this is a solid, so that's not an elemental form, plus H2 gas. That is an elemental form. It's going to produce 2 Fe solid iron, elemental iron, plus 3 H2O. That's going to be in liquid form, which is not elemental. So just going through here, those are going to be 0. And I have to look up what is the change in enthalpy for liquid water and this Fe2O3. Switching back, we can look for, I should go up. Here's Fe2O3 solid, which is what we're looking for, negative 824.2 kilojoules per mole. I should have said we also have up at top we had 1 mole of that, so I'm just going to, there it is. For part B, we had 1 mole of the silicon tetrachloride, so I just took off the per mole in my final answer. So the H2O is the other one I have to find. H2O would have hydrogen. I think that's up towards the top. Nope, I must have missed it. So you can also just do a quick Control F and type in hydrogen. There it is. And you can see the liquid and the gas. They're similar, but they're a little different as well. So in this case, we're looking for the liquid. That's negative 285.83. Kilojoules per mole. And we need to multiply that by 3 moles. Because there's a 3 right there. So to find this, now we have that 3 times negative 285.83 kilojoules per mole. But we need to subtract from that a negative 824.2 kilojoules per mole. And really that's a mole, and really we're multiplying this guy by 1 mole. So the units there, all my moles cancel. And I'll end up with a delta H in kilojoules. I can't see. There we go. Sorry. So I've just rewritten, this was the delta H I found off that chart for liquid water. I multiplied it by 3 moles. This is the delta H I found for iron 2 or Fe2O3. I then took my products here. I'm subtracting from that my reactants. So to do the math, multiply that by negative 285.83. We subtract from that a negative 824.2. And I end up with negative 33.29. Kilojoules. So using the table, it makes these types of problems pretty easy. The key is to remember subtracting the products from the reactants. No, the other way around. Products minus the reactants, or subtracting the reactants from the products. And one last one before we go. This is part D. We have 2 lithium hydroxide solid. We're adding to that CO2 gas. And that's going to produce lithium 2 or dilithium. There we go. And this is a solid plus H2O gas. Since we're running a little short on time, you can look these up on the table. That's where I got these values from. I got negative 487.5 kilojoules per mole, negative 393.51 kilojoules per mole, negative 1216.04 kilojoules per mole, and last, negative 241.82 kilojoules per mole. And now we just have to multiply everything out by their stoichiometric ratios, basically just pulling down this 2 times that guy and canceling all my moles out. Make sure we do the summation of the products. So that's negative 1216.04 kilojoules minus 241.82 kilojoules minus 2 times negative 487.5 kilojoules minus 393.51 kilojoules. Okay. And since I'm subtracting and both of these values are negative, I'm going to go ahead and make everything positive. Just makes my life a little easier. And now we can just plug into our calculator. Negative 1216.04 minus 241.82 plus 2 times 487.5 plus 393.51. And I get there a negative 89.35. Joules, or kilojoules even. Want a little bit of space there. All right. And that's my answer for part D. So all of those are fairly straightforward. It takes a little bit of math to do them, but once you get the process of them down, basically following this type of equation, it's pretty simple. So definitely check out Appendix G in the textbook or any other resources. You can do a quick Google search of these types of values as well. Thank you all for watching. Definitely check out our YouTube videos for the past videos, or if there's anything that you didn't quite understand from Chem 221, check out the videos that we have for that as well. I also am going to have Saturday 2 p.m. live streams, and right after that live stream up until 5 p.m. I'll have drop-in tutoring hours through the Penji app. Just log on to web.penji.com and sign in with your PSU account information. You should have tutoring access to all of our tutors there. You can also schedule a tutoring appointment with our chemistry tutor Amir, and he's happy to help you out as well. Best of luck and enjoy.